Alright, so what's interesting here about these curves is that if you look at these different curves, peak volumetric efficiency and minimum timing occurs at different locations for the three different setups. I mean, the factory car, peak VE is probably around 4,000 RPMs. You can see how this dips compared to this graph. For the nitrous injected car, peak VE is also at that same point because this is where we release the nitrous shot. And for the supercharged car, we actually see a wide range where we have good volumetric efficiency between 3,000 and 5,000 RPMs, but in the top end, the car doesn't make as much power as it could actually if this efficiency were flat, but because we lose volumetric efficiency above 5,000 RPMs, the car is a little down on power, and that means we can advance the timing a little bit to make up for that loss of power. The thing is here, this is measuring volumetric efficiency, which relates right back to that mixture density that we just talked about. The higher the density, the less timing you need to keep the mixture safe. The lower the density, and the lower the volumetric efficiency, such as our example here on the high RPM, the supercharger isn't as efficient or the exhaust system isn't as efficient as it needs to be. The volumetric efficiency drops a little bit, the mixture is less dense, you can add a little bit more timing to make more power. Also in the nitrous example here, when you release a 100 shot at 4,000 RPMs, you're releasing 100 additional horsepower on 260 horsepower, so that's about 50% increase of volumetric efficiency, so you need about 7 degrees of timing retard. But as you go out towards 6,000 RPMs, then 100 horsepower shot on a 350 horsepower engine, that's only about a 30% increase in volumetric efficiency, because that nitrous gets distributed with a lot of other air, so the density is lower. And so what we can do here is we can advance the timing a few degrees compared to here and get a little bit more power out of it. And all of the racers know this when they use nitrous, especially if you're using a very large shot of nitrous like a 200 shot or 250 shot. When you start out that run and you hit the nitrous, the first initial hit, you might get 250 horsepower, but as you go down the track, the bottle pressure will drop slightly because you're using such a high flow rate of nitrous, and so the volumetric efficiency will start to drop too, and so you can add a little bit of timing on the top end, and the car will still be safe because the mixture is less dense and it can take a little bit more timing, and that'll give you a little bit better times. So the key here is to tailor your timing map, not just a base retard or a flat line retard. You want to retard differently in different RPMs to get the most horsepower out of your setup, depending on what volumetric efficiency is already in there. And this might be a little hard to read, so I'm going to show you this in terms of just absolute retard. You can see for nitrous we want the maximum retard where we have the maximum volumetric efficiency, which is close to where we release the nitrous shot, and then we can have a little less retard in the higher RPM ranges. But for a centrifugal supercharger, boost builds with RPM, volumetric efficiency builds with RPM, and so timing retard needs to be proportional to boost, which will give us the best power results. If I go out and give 8 degrees of timing retard at 2,000 RPMs because the car is supercharged, then between 2,000 and 6,000 I'm going to be losing horsepower because I could have more timing in it, and I'm not. So with this little simulation you can figure out what your timing curves look like. I mean, the numbers aren't exact because timing numbers differ from one engine to another, from one octane level to another, from one compression ratio to another. But what's important here is the trend. Is it increasing? Is it flat? Does it dip at any point? And where your minimum and maximum points are, because that'll help you tune your setup faster. When you're renting out dyno time, you can know ahead of time, or by simply plugging in the numbers that you get from your dyno operator into the next version of the power calculator, which is going to have this Excel sheet built into it. You're going to be able to look at your timing trend and compare that with your actual timing map and figure out how to do quick adjustments. Last thing I want to show you here is a timing map for a turbocharged Toyota. As you can see here, if I look at a load cell and I go into this whole row, the RPMs change from 400 RPMs to 8,000 RPMs, but at the same load I can see here my mechanical timing increasing with RPM. And then as I go down here with boost, I can see my timing drop with boost. As you can see, I started at 21 degrees and I drop with boost pressure. That's because of the density of the mixture. And then as I go across here at about 15 psi, I see a minima around 2800 RPMs, and that's where my peak VE is.